Questions before we continue with this. You wanted to ask something. That was to show you that the solution is a wave. But that does not mean in your numerical simulations you will assume solution to be of that type. That has nothing to do with the numerical work. That was only to show you that the equation we are studying is a wave equation. That there is a travel, the wave will propagate at the speed c, which is square root of e over rho. So if you solve the problem numerically, your wave speed does not come out to be close to c, that means the code is not right. Okay? So when we do the problem numerically, we have not done it yet. All we have done is we have reduced the partial differential equation to a system of coupled ordinary differential equations. But we have not solved them yet. So it's more or less halfway done because we still have to solve them. Excuse me. Also, we had initial conditions, which we have not, we need to translate those initial conditions on U because we had initial velocity given and initial displacement given. We need to translate those into D's, conditions on D's. Incidentally, what is D1 equal to? Supposing we solve the problem. So what will be the meaning of, or physical meaning of D1 or D2 or D3 or D4? Displacement of point 1. In this case, we are not talking about deflection, it's axial displacement. So that will be axial displacement of node 1, axial displacement of node 2, axial displacement of node 3. So what should happen is that supposing node 1 is displaced at time 0, you should see that node 2 is displaced by the same amount after time c over h, he over c. H is the distance, c is the wave speed. So if node 1 is displaced by, say, 1 centimeter at time 0, this one should be displaced by 1 centimeter after this time. This node should be displaced by 1 centimeter after 2 he over c. And if it doesn't happen, close. You will never get exactly the same except in one case. I don't think we will be able to do that because it requires some more math or some more analysis. So except for that case, generally you will get close. Like if it's supposed to be 1 millisecond, you might get 0.95 or 1.05, something of that type. But if you get too far off, that means the code is not right. And also, supposing you, at this node, you give a pressure profile of this type. So this is the boundary condition, and this is time. You start at 0. This is say 1 microsecond, and this is 2 microseconds. So if our solution is right, if our code gives you correct solution, this triangle should propagate. From left to right, it should get reflected back, depending upon the boundary conditions here, whether it's fixed or free, and then it should keep on propagating forever. But that does not happen in numerical work. Okay. So remember, we don't have any dissipation. It's an elastic system. So it's really a spring mass system, and in theory, it should keep on vibrating forever, or this pulse should keep on going back and forth forever. But unfortunately, our numerical algorithm, which we have not talked yet, we have not talked about time integration yet. that introduces dissipation into the system. Our numerical time integration scheme introduces dissipation into the system, and therefore the amplitude keeps on changing and the wave shape keeps on changing. So the challenge in numerical work is for this wave shape, triangular wave shape, to be maintained as triangular wave shape. That's what the analytical solution gives, but numerical solution does not do that. That's a fact of life, and people have spent time, well, years and years to figure out algorithms that will preserve the shape of this wave. So in one case, yes, if you choose your time step size, if you choose your element size correctly, and there is one more thing, then yes, numerical solution should exactly reproduce this wave, but otherwise no. Okay, so let's first try to translate our initial condition onto D. So there are two ways to do it, because you are given U at x equal to, at time t equal to 0. So you are given U0. So you are given U at x equal, at time t equal to 0 as U0 of x. Okay, this is supposed to be given to you. So if you set here, first you set time t equal to 0. So what we have is U0 of x, and then this will become 0. So can I solve this equation for di? How will I get di from this equation? Yes? I want to find the value of D10, D20, D30, and D40. I want to find the value of at time 0 of displacement at this node, this node, this node, and that node.
X equal.
Yes, very good. You set x equal to xi or x equal to xj. What will happen is if you set x equal to the coordinate of the node, it will be either 1 or 0. So one possibility is that we can say di of 0 equal to u0 of xi. And if you are given the initial velocity, so that's v0 will be d dot here. You first differentiate and then set time equal to 0. And again, by the same reasoning, then d dot I0 will be v0 of xi. Does it make sense? Sometimes we, instead of doing this, we do what I'm going to do now. So you are given u0 of x, and I have psi I of x di at time 0. So we multiply both sides by rho psi j of x. Multiply both sides by rho times psi j and integrate this from 0 to L. So if we do that, this one comes out of the integral sign because there is no x in it. There was no x in it, so it came out of the integral sign. Do you see this thing somewhere on the chalkboard? It's mass matrix. So we can call this thing, say Fj. We are just denoting it by Fj. You know this function, you know these functions, you can evaluate this integral. So what we have done is Mij dj0 is Fi0. I interchange I and j. That should not cause any problem because M is symmetric. So now you can solve for d0. This is some kind of smoothing technique that you have smoothed out the initial displacements and found the values at different nodes. So the difference is, if you follow this approximation, first of all, is it clear what we have done? So if you follow this approximation, then you initially disturb only node 1. You will see from that this node is also disturbed, because mass matrix is not necessarily diagonal. So you will see initially all of these things have been a little bit perturbed. But if you follow the previous method with this one, then only node 1 is perturbed. So, yes, for now. Pardon me? Okay, we were given u0x equal to, we were given the value of u0x. So since I don't have enough room here, I can write here. So we were given u0 of x. So if you plug in time equal to 0, this should be equal to psi I of x di of 0. Right? That's from this expression here. So you multiply both sides by rho psi j. There's nothing wrong in multiplying both sides, right? Now you integrate it. From 0 to L. This integral we can evaluate because you know the function, you know the basis functions, you know the mass density, so you can evaluate this. This one psi I psi j times rho, you have already evaluated in here. So what we are doing is we are writing now this thing as Mij dj0 equal to Fy0. Pardon me? No, this is fine. I just changed I to j. M is symmetric. Mi is same as Mji. then you can do the same thing for velocity term. The only difference is this function u0 will be replaced by v0. So there are two ways to find the initial conditions. At least two ways. Both will give you different answers. So the two will not give you the same answer. The hope is that if you find the solution for after a long time or a large enough value of time, then the effect of initial conditions will not appear. But otherwise it will show up. If you just start the solution at time 0 and want to find the solution at the next time step, you will see the effect of the initial conditions. But if you find the solution at, say, 1000th time step, which I have not talked about what is the time step yet, then you won't see it, hopefully. Okay, so the idea is that from the given partial differential equation and the initial conditions, we have reduced it to an ordinary differential equation for the nodal accelerations. These are accelerations, and they are coupled, and you can find the initial values either this way or this way. Either, not both ways, just use one of the two. Okay, now let's see how does this M look like. What about K? So who will tell me if I am on element 1? So what will, well, for a typical element, what will K11 look like? K11 is this matrix. E is, let's assume E is constant. Pardon? E by L. No, there is no A. A is already gone. Area is gone. You have done it. 1 over HE, so it will be E over HE1 minus 1 minus 1, 1. When we drive this, so you will then assemble it, so you can get the global K. So it's basically 1, minus 1, 2, minus 1, and so on. What about the other one now? Mass matrix. So let's evaluate that to show you how it looks like. Is it okay? This is all we are doing is replacing thermal conductivity K by the modulus E. Nothing else is changed. And so M11 on element, so this will be rho psi 1 square dx. And if I am on, say, element 1, this element, then I'm going to integrate from 0 to HE. Right? So I'm on element 1. Rho is constant, so we can take it out. What is the expression for psi 1? What is the expression for this function? So this is HE minus x over HE. No, yeah, when x equal to 0, this is 1. And when x equal to HE, this is 0. So that is the equation of psi 1. So we need to square it. So it's HE minus x over HE square dx. So it's capital X. If you integrate it, so you get rho over HE square, HE minus X cube over 3 times minus 1 from 0 to HE. I guess it's not hard to integrate this x, a minus x square. So at the upper limit, 0. At the lower limit, HE cube, then minus and minus will cancel. So we get rho HE over 3. Is it okay? So I'm going to raise it and then write M12. That will be rho times psi 1, psi 2. Again, rho is outside. This one was HE minus X over HE. And the other one goes from 0 to 1. So that's X over HE. This function, let me pick up the red pen. This one is X over HE. X is 0, 0, X is HE, 1. So now we have to integrate this. So we have rho over HE square, HE x square over 2 minus x cube over 3 from 0 to HE. Oh, I'm sorry? Oh, this is M12, yeah, oh. I did not write. You are right. M1. Thank you. So if we at the lower limit, this is 0. So at the upper limit, this is rho over HE square times HE cube, 1/2 minus 1/3, and that's 1 over 6. One half minus 1/3 is 1 over 6. So can I erase it? I see she's still writing, so I'm waiting. Done? So M is symmetric, so I don't need to find M21. If you interchange I and J, same. Now M22, believe me, same as M11. So mass matrix is rho HE 1/3, 1/6, 1/6, 1/3. If you add all 4 entries, 1/3 plus 1/3 plus 1/3. So you get 1. So the mass of the element, if you look at the length, is HE. Area of cross section has already been taken care of. So it should be rho times HE. And if you add them up, you get rho times HE. So if you now find the total mass matrix, so let me take out 6 here. So this will be 2, 1, 1, 2. So 2, 1, 1, 2. Again, if you add them up, 6. So if you now, I want to assemble it. So it will be 4 by 4. We took 4 nodes. So this is going to be 2, 1, 1, 2. Now if you go to the next one, you will get 2, 1, 1, 2, 1, 2, 1, 1, 2, 2, 1, 1, 2. So, does it make sense? Shakti, you don't like it. Okay? So, the idea of showing this to you is that the equations are now coupled, like md double dot is going to be rho he over 6, 2, 1, 1, 4, 1, 1, 4, 1, 1, 2. The entries I did not write are zeros. And this one is going to be d1 double dot, d2 double dot, d3 double dot, and d4 double dot. So acceleration of node 1 and node 2 are coupled, then 1, 2, and 3 are coupled, 2, 3, and 4 are coupled, then 3 and 4 are coupled. And of course, if you keep on going, then every time what you see is there's a coupling between, if you are here, this node belongs to 2 elements. So it belongs to both these elements. So the acceleration of these 3 nodes is coupled. If you go to this one, this node belongs to these 2 elements. So the acceleration of these 3 nodes is coupled. So this mass matrix is called consistent mass matrix. No, it is. Yeah. Otherwise, I will be in trouble. 2 plus 1, 3, 4, 8, 9, 10, 14, 15, 16, 18, divided by 6, 3. And we have 3 HE there. If we do meshless methods, then you will see that the total mass will not be equal to the mass of that length. Because in meshless methods, you have overlapping regions. I don't know where we will end up, but that's what happens. In a meshless method, you won't get that part. Okay, but that's again jumping the gun, going further. Now, when we will write the integration scheme, we will like to uncouple the acceleration of node 1 from the acceleration of node 2. So if we want to do that, we use lumped mass matrix. Lumped means lump, okay? So there is no coupling between 1 and 2 there. So one way to get that lumped mass matrix is, remember, we cannot change the total mass. So if you add rows, first row, add whatever you see in the first row, put it M11, and then remaining are zeros. Lumped means you are going to diagonalize it. First row, add all of them up, put at M11. Second row, add all of them up, M22. So it's 0, 6. Third row, same thing. Fourth row, same thing. So the total mass has not changed. We have played a game. It is not consistent with what we derived. We derived this. We changed that to that one. Pardon me? Oh, yeah, sorry, you are right. Sorry, I did not copy that row. Yeah, you are absolutely right. Row H over 6, yes. The outside term does not change. Yeah, you are right, thank you. Row H over 6 was outside, I need to copy that. Yeah. Otherwise, everything will be off. But now if you add them up, you still have the same. So what this one does is, as far as the accelerations are concerned, you can solve for the acceleration of node 1 without worrying about the acceleration of node 2. However, don't think that node 1 and node 2 are not communicating with each other. They are. They are communicating through this one. They are communicating through this. We do not diagonalize K. We are not diagonalizing K. We are only diagonalizing, in some cases, if you want, I will show you when it is preferable to diagonalize M. Okay. So if we diagonalize M, we call it lumped mass matrix, and we never diagonalize K. Never. Otherwise, you don't have any coupling between node 1 and node 2. So the node 1, that coupling between node 1 and node 2, that spring we have, is coming through this K. That E term here. Remember we wrote E over HE 1 minus 1 minus 1 1. So they are coupled. So the coupling is coming through those K terms, not we have one couple through the M terms. It's an approximation. Remember, we are seeking an approximate solution of the problem. We want to make our life as simple as we can. And one reason we do that is, you will see in a little while, well, maybe tomorrow, that it will be a lot easier to use this than to use this. Okay, so now, actually, many times lumped one gives you better solution than the consistent one does. There is another mass matrix which is neither consistent nor lumped, gives you exact solution of the analytical problem. But I'm not going to talk about it because I have to stick with the advertisement. The advertisement does not say higher order mass matrix. But that one is in the notes, and the proof is there in the notes that if you use a higher order mass matrix, then the numerical error is 0. So you get exactly the analytical solution of the problem. But that will take like 3-4 hours to prove it. And I don't think we can afford that much time. Okay, so, yeah? Pardon me? Yeah, yes. Oh, so I think you are suggesting we should quit. Okay, let's go. Yeah, sure, I can quit. Sure, sure. Okay, good. Thank you. Yeah, I can quit. Thank you.